Hello, it's Mr. Tuxford here. Let's go through this question on collisions in space. So, comets and asteroids are loosely formed objects that are easily broken up, especially when they collide. We're told the mass of one of them is 1 times 10 squared. So 10 squared is 100, so 100 kgs. Let's just put that in. Moving at a velocity of 500 meters per second, and it collides with a stationary 300 kg object. Alright, so we're given masses, one velocity, and then we're told one is stationary, so that its velocity is 0 in this reference frame. And we're given this diagram before the collision. So we should immediately be thinking center of mass, gravity, momentum, right, if it's going to collide. In question A, calculate the distance of the center of mass from this object, from the 300 kilogram object, when they are, 4,000 meters apart. So it's a center of mass calculation question. So you should start by looking in your formula sheet and recognizing the center of mass equation. So let's write that out. So look in your formula sheet for x, COM. So x is just for a distance or a displacement. COM in the subscript center of mass is equal to mass 1 times displacement 1 plus mass 2 times displacement 2 all over the sum of the masses. So effectively this is a weighted average. And now the tricky bit is deciding what's what. Since it asks for the distance from the 300 kilogram object, we will define this as our origin right here. So this is our x0, our starting point. And so let's call this M1 and this one M2. So M1 can be the smaller mass in this case, which is 100 kilograms. And x1 is its distance from our origin. Oh look, it doesn't even recognize my straight line there. The distance from our origin, and what is that? Well, that is the full 4,000 meters. Plus M2, well that's our larger mass, which has a mass of 300 kilograms, times the distance of M2 from the origin. But since we define the origin as on M2, that distance is 0. Right? It is 0 meters from its own center of mass, right? From itself, which is nice because this whole term goes to 0. Right? But I'm showing that step regardless, all over the sum of the masses, 100 kilograms plus 300 kilograms. And so if you punch that in on your calculator, whoop, here we go, menu, run math, so you can put a fraction, oh, mine's a little bit older, 100 times 4,000 equals 400,000, makes sense. We divide it by 100 plus 300, closing off our brackets, to give 1,000. 1,000 meters. Alright, so the center of mass is about here. And let's just do a sanity check. So if that's 1,000 meters, we're left with 3,000 meters on this side. And since M2 is 3 times as heavy as M1, when we split the ratio into 3 to 1, right, it adds up to 4,000. So that's another way you could have solved this problem, is just by a pure ratio. But doing the full calculation works for when the numbers are a bit more fiddly. Alright, and that's an achieved question. Alright, question B. Calculate the gravitational force between them when their centers of mass are 10 meters apart. So they're very close now. They still have a mass and they're still a distance apart. So we can calculate the gravitational force. So looking at your formula sheet, F, you could do subscript G for gravitational force, is equal to the gravitational constant times the product of the masses divided by the distance between them squared. Now capital G is the gravitational constant. It's not acceleration due to gravity, but it's a constant anywhere in space, no matter what bodies are around with the different masses. And that is on your formula sheet with a value of 6.67 times 10 to the negative 11. Let's put that in brackets. Capital M and lowercase m, these are the two different masses. In this case, well, in every case, it doesn't matter which order you put. Conventionally, capital M is the larger mass. So I'll put the 300 kg object times the 100 kg object. And that is all over the distance between them, 10 meters, and that is squared. So don't forget to square it. And punching that in on your calculator, being careful you're using brackets and following BEDMAS, you should get 2.00 times 10 to the negative 8 newtons. Awesome. And if you just got that correct force, that is an achieved point. Alright, so that is a very small force. But does that make sense? Well, they aren't that heavy, right? 100, 300 kgs, obviously I can't really lift that, but in the scheme of celestial bodies, that's quite light, and they're very close together. So the closer they are together, the stronger the force. However, the lighter the mass, the weaker the force. Alright, and part 2, hence, so we need to use our previous force value. Find the acceleration of the 100 kilogram object. So we're looking for acceleration, we know the mass, we found the force, we should be thinking Newton's second law, F equals ma. And then further it says, determine if the assumption that their velocities are constant before the collision is valid. Okay, so let's start by finding the acceleration. So I'm going to start by writing F net equals mass times acceleration, Newton's second law, where assuming this is the only force, Fg, right? We can ignore friction, in space, that's a fair assumption. Let's just rearrange it for acceleration first. So F divided by m, substituting in 2 times 10 to the negative 8, all divided by the mass, which was 100, giving us an acceleration of 2 times 10, what's that, to the negative 10, right, just dividing by 100. Meters per second squared. Awesome. So if you got this and not the force, for example, you got the wrong force but the correct acceleration, that would be an achieved point. But let's finish off this question. So determine whether the assumption that their velocities are constant is valid. Okay. So they've come closer together. They're 10 meters apart, and we've assumed that their velocities are constant. Well, we've just shown that the 100 kg object is accelerating. We could also show the same for the 300 kg object. So I'm going to write invalid assumption. Since they are both accelerating. And full stop. What else could we add? We could, let's link it back to the question, right? So their velocities are not constant. Always answer the question, right? I gave the reason, but now I just answered the question, so it's invalid. They are accelerating, so their velocities are not constant. Awesome. And so if you got both the force and the assumption correct, that is a merit. The other way to answer this question is, since the acceleration is so small, like times 10 to the negative 10, that's very small, you can assume it's about constant, right? You could say that too. All right, on to part C. Okay, they finally collide with no external forces. So what should you be thinking? You should be thinking momentum is conserved. Cool. And they form two rocks, A and B, each with the same mass of 200 kgs, and they move away with 20 degrees north and south of the horizontal. Okay, so it's a symmetrical system. Question is, show that the size of the momentum of rocks A and B are the same, even though they are in different directions. Awesome. Multiple ways to do this one. Let's just go for the common sense method. Well, you can say that about all of physics, but some of it's not common sense. So before the collision, let's have a look again. What is the total initial momentum? Well, mass 1 has a mass, great, and it's got a velocity to the right. So its momentum is to the right. Mass 2 is stationary, so its initial momentum is 0. So the total momentum is to the right. So that's the initial momentum. So let's write that down. Initial momentum, Pi, is to the right. Cool. All right, so that's before. Now afterwards, the final momentum must also be to the right. And that's because momentum is conserved. So P is conserved. So PF is to the right. Cool. Which means A and B, even though they've gone off at angles, their vertical components, right, the up and the down component, needs to be equal and opposite so that they cancel each other out, and we're only left with a momentum to the right, a total momentum to the right. So let's put that in a sentence. This means that the vertical components of PA and PB must be equal. So that accounts for the vertical components. What about the horizontal components? Well, they have the same mass and are traveling at the same velocity. Can we assume that? Doesn't say in the question, right? But since they're at the same angle and they have the same vertical components with the same mass, they must have the same horizontal components. So let's write since angles are both 20 degrees. All right, symmetrical. PA must equal PB. Awesome. So just to summarize that one, the initial momentum is to the right. We know momentum is conserved, so the final momentum must be to the right. Now A and B are going at angles off of the right, which means their vertical part, so the up and the down, parts of their momentum must be equal. And since it's symmetrical, since they're both at 20 degrees, it means their individual momentums must be the same. All right, and that is a merit question. All right, on to question D, the excellence part. And so this one is to actually find the speed of the rocks, A and B. And of course, in part C, we just said that the momentums of A and B would be the same, which will simplify our calculations. So, bit hard to write today. Let's go before the collision and after. I find diagrams extremely helpful for momentum problems. So before the collision, what is the initial momentum? So PI, initial momentum, recall, well, let me just painfully scroll up one moment. All the way here we go. So the initial momentum is caused by this mass and its velocity only, because mass 2 is stationary. So momentum, initial momentum would be 500 meters per second times 100 kilograms. Let's write that in. So just write M1 V1, which, what did I say, 100 kilograms times 500 meters per second, which is, what's that, 50,000? 500, 5,000, 50,000, yep. And what are the units? Well, mass is in kilograms, speed is in meters per second. Awesome. Now momentum is a vector, so it needs a magnitude and a direction. So I'm going to just remind myself this is to the right. My diagram also shows that. Cool. All right. Now after the collision, let's have a think. We have momentum of A plus momentum of B. So a reminder, momentum is a vector. So when we add momentum, we don't simply add the size, we need to account for the direction. So when adding vectors, you can, if you like, add vectors like this, and draw this part here, that would be the sum. But how I've done it in my class is we add head to tail, like so. So that's PA, that's PB. So I just moved the vector that was here and translated it so that its tail starts at the head of A. And that vector sum, drawing's a little bit off, that's fine, is equal to the final momentum, which is the same as the initial momentum, because momentum is conserved. And so straight away we can actually label the size of PF as 50,000 kilogram meters per second. Alright, what else can we label? We can label this angle as 20 degrees. Yeah. Now what would that angle be? Would that be 20 degrees as well? We don't even need that, because what we can do is split this into a right angled triangle, like so. And we know, since PA and PB are the same, this bottom length, the horizontal component of PA, will be 25,000. Yeah, and with that, you'll notice we have a right angled triangle right here, with PA being the hypotenuse. That's what we're looking for. We have the angle and we have adjacent. So we can solve for PA. So solving for PA, we have adjacent, looking for hypotenuse, so we'll use cos of the angle equals adjacent over hypotenuse. So multiply PA across, divide cos 20 across, PA equals 25,000 over cos 20, and that works out to be, one moment, oh, am I in degrees or radians? I'm in radians. Top tip, always check, even between questions. So 25,000 divided by cosine of 20 degrees to give 26,604 kilogram meters per second. Let me just scroll down a bit. So PA equals PB equals 26,604 kilogram meters per second. Now, have we answered the question? Nope. It's asking for the speed of the rocks. We have found the momentum. So our last step is just to recall momentum depends on mass and velocity. So velocity, or speed if we're not including the direction, is momentum divided by mass. So VA must equal VB, right? They have the same momentum, they have the same mass, which is 26,604 divided by, what's their mass? Was it 100? Nope, it was 200. Good thing I checked. Always double check. Divided by 200, giving us, so divided by 200, 133 meters per second. And that is an excellent question. And so let's just step through this one more time. So this momentum question is symmetrical, which does make it a bit easier. So before the collision, we calculated the total initial momentum, which only depended on mass 1. So m1 times v1 to give 50,000 kilogram meters per second. What I didn't write here, which I definitely should have, is pi equals pf. Since momentum is conserved. Right? I implied it by writing PF as 50,000, but it is worth stating. Right? So before the collision, we have an initial momentum. Since momentum is conserved, after the collision, PF, that green arrow, is the same size and the same direction. But that final momentum is made up of the vector sum of A and B. And it doesn't matter if you draw A or B first, right? If we drew B, we'd go down and then back up, exactly the same. I drew PA and then I added PB. I labeled 20 degrees. Yeah, we could have also labeled this is 20 degrees, right? It is symmetrical like that. However, I just split it into one right angled triangle, and I found the horizontal component, which was 25,000, right? Half of 50,000. And so I made a triangle that looked like this. 25,000, 20 degrees, and I could solve for PA, right? Using cos of the angle equals adjacent over hypotenuse, rearrange for hypotenuse to get 26,604 kilogram meters per second. And notice PA is more than 25,000, which is why it was a vector sum rather than a scalar sum. So just keep that in mind. Again, since it's symmetrical, right? We found previously that PA would equal PB. So I just restated that, stated the momentum equation, solved for velocity, or rather speed, but according to our diagram, we know the direction of its velocity regardless. And there you go. Excellence in the back. All right, I'll see you next time.